Hello, folks. So, this is part 12 of learning Rust from scratch. And in this video, we're going to just go ahead and continue reading through the book, the Rust official book, which is the Rust programming language book. And we are on chapter 3. So, in third chapter, basically, we're going to be reading about common programming concepts like variables and mutability, so ability to mutate and change or data types, and then we'll also be looking at functions, comments, and control flow. So this chapter covers concepts that appear in almost every programming language and how they work in Rust, right? So I have learned some languages, like for example, I started off with C and C++, and then later I learned some Java. I've learned a bit of PHP, and yeah, I know a bit of HTML, JavaScript, and CSS, and then I've learned Golang later. In between, some Ruby and Python also. Um, so yeah, and other languages for configuration and all, for example, YAML and all. So let's go ahead and let's look at how Rust implements or has these concepts in Rust itself. So many programming languages have much in common at their core. None of the concepts presented in this chapter are unique to Rust, but we'll discuss them in the context of Rust and explain the conventions around using these concepts. Specifically, you'll learn about variables, basic types, functions, comments, and control flow. These foundations will be in every Rust program, and learning them early will give you a strong core to start from. So the core has to be strong, the core concepts, and also yeah, will give us a strong core understanding, foundational understanding of how things work in some basic stuff in Rust. So Rust language has a set of keywords that are reserved for the use by the language only. So these are standard keywords. It's called think keywords or tokens, right? And these are like registered tokens or taken tokens, and you can't take them or you can't use them. It's like not for use. So much as in other languages, keep in mind that you cannot use these words as names of variables or functions. Most of the keywords have special meanings, and you'll be using them to do various tasks in your Rust programs. So a few have no current functionality associated with them, but have been reserved. So they're reserved and registered. So it's reserved only for the language. For functionality that might be added to Rust in the future, you can find a list of the keywords in Appendix A. So this is the list of keywords, basically all the reserved words, as async, await, break, const, continue, create, dynamic dispatch, dyn, else, enum, extern, false, function, for, if, implement, in, and whatnot, right? So there are so many. Keywords reserved for future use: abstract, become, box, do, final, gen, macro, override, priv, I don't know what is clear. Try, type of, unsized, virtual yield, raw identifiers are the syntax that lets you use keywords where they wouldn't normally be allowed. So you use a raw identifier by prefixing a keyword with r hash. Match is a keyword. If you try to compile the following function that uses match as its name, then you get an error. So found keyword match, expected identifier. Okay, so instead you put r hash, I think. So the error shows that you can't use the keyword match as a function identifier. To use match as a function name, you need to use the raw identifier syntax like this. And this code will compile without any errors. Note that on the function name in this definition, as well as where the function is called. Raw identifiers allow you to use any word you choose as an identifier, even if that a word happens to be a reserved keyword. This gives us more freedom to choose identifier names, as well as lets us integrate with programs written in a language where these words aren't keywords. So, in addition, so basically it lets us integrate with programs written in a language where these words aren't keywords. In addition, raw identifiers allow you to use libraries written in a different Rust edition than your create uses. For example, try isn't a keyword in the 2015 edition, but it is in the 2018, 2021, and 2024. If you depend on a library that's written using 2015 edition and has a try function, You'll need to use the raw and fair syntax try in this case to call that function from your 2018 edition code. So raw and has allowed you to use libraries written in different class editions than your current uses. Okay, so see appendix C for more information on editions. So yeah, you can check out about editions. I'm gonna check it out later. So for more details, check out the edition guide, and there is an edition guide, right? So let's actually go back from appendices to this. So variables and mutability. So as mentioned in the storing variables, storing values with variables section, by default variables are immutable, so you can't mutate them. You will not be able to mutate them. This is one of the many nudges Rust gives you to write your code in a way that takes advantage of this safety and easy concurrency that Rust offers. However, you still have the option to make your variables mutable. Let's explore how and why Rust encourages you to favor immutability and why sometimes you might want to opt out. When a variable is immutable, once a value is bound to a name, we can't change that value. To illustrate this, generate a project name variables in your projects directory by using Argo new variables. Then in your new variables directory, open source main and replace its code with the following code, which won't compile just yet. So let's actually try that out. Um, learning Rust, Argo new variables, and let's open that up. And let's actually say memorize. So does this compile? We can enable Rust Analyzer here. So yep, enable workspace and it should error out in some time. Did it index? So it gives an error. It says cannot assign twice to immutable variable x. So x, the value of x is this. Cargo check is an error. So this is 0384. Cannot assign twice to immutable variable x. So how about I do this? Let x. Can I do that? I can't do that currently. So once it's assigned, you can't assign it again, I think. So save and run the program using cargo run. You should receive an error message regarding an immutability error as shown in its output. In this output. So this example shows how the compiler helps you find errors in your programs. Compiler errors can be frustrating, but really they only mean your program isn't safely doing what you want it to do yet. So they do not mean that you're not a good programmer. Experienced Rustaceans still get compiler errors. So they're just trying to ensure that your morale is not going down. And you receive the error message cannot assign twice to immutable variable x because you tried to assign a second value to the immutable x variable. It's important that we get compile time errors when we attempt to change a value that's designated as immutable because this very situation can lead to bugs. If one part of our code operates on the assumption that a value will never change, and another part of our code changes that value, it's possible that the first part of the code won't do what it was designed to do. Um, okay, operates on assumption won't do what it was there because of this kind of work. And so basically, they're talking about how one part of the code operates on the assumption that a value never changes, and another part of our code changes that value. It's possible that the first part of the code won't do what it was designed to do because the value changed, because this is depending on the assumption that the value will never change, right? The cause of this kind of work can be difficult to track down after the fact, especially when the second piece of code changes the value only sometimes. The Rust compiler guarantees that when you state that a value won't change, it really won't change, so you don't have to keep track of it yourself. The code is just easier to reason through. So basically, this is about how values of a variable, the variable's value can change throughout the program, and when it changes, that's where errors occur, and you won't even know the history of the different values of the variable, and that can be problematic. So it's better to not mutate and instead have different variables and whatnot every time you are trying to create a new value, or override the existing variable with a new variable and shadow it uh, if you don't want to mutate it, but you're just trying to reassign or something, doing some conversion and all. But mutability can be very useful and can make code more convenient, right? All the variables are immutable by default. You can make them mutable by adding mute in front of the variable name, as you did in Starter 2. Adding mute also conveys intent to future readers of the code by indicating that other parts of the code will be changing this variable's value. When we run the program now, we get this. So we have the mutable. So we are allowed to change the value bound to x from 5 to 6 with when mute is used. Ultimately, deciding whether to use mutability or not is up to you and depends on what you think is fairest in that particular situation. Constants like immutable variables, constants are values that are bound to a name and are not allowed to change, but there are a few differences between constants here. First, you're not allowed to use mute with constants. Are just immutable by default, they're always immutable. You declare constants using the const keyword instead of the let keyword, and the type of the value must be annotated. So we'll cover types and type annotations in the next section. So don't worry about the details right now. Just know that you must always annotate the type. So they're telling unsigned filter with user. The constants can be declared in any scope, including the global scope, which makes them useful for values that many parts of code need to know about. The last difference is that constants may be set only to a constant expression, not the result of a value that could only be computed at runtime. So here's an example. So this is 3 hours in seconds, 60, 3 hours, 3 into 1 hour is 60 minutes, 60 minutes, 1 minute is 60 seconds. So in seconds. So the constant name is 3 hours in seconds, and its value is set as a result of multiplying 60, the number of seconds in a minute, the number of minutes in an hour, and the number of hours you want to count in this program. Thus, naming convention for constants is to use all uppercase with underscores between words. This is pretty standard, common. The compiler is able to evaluate a limited set of operations at compile time. Um, let's just choose to write out this value in a way that's easier to understand and verify rather than setting this constant to the value 10,800. See the references section on constant evaluation for more information on what operations can be used when declaring constants. Constants are valid for the entire time a program runs within the scope in which they were declared. So if they are declared in global, so it will be available for the entire time the program runs within the global. So and this property makes constants useful for values in your application domain that multiple parts of the program might need to know about. Um, makes constants useful for values in the application domain that multiple parts of this program might need to know about, such as the maximum number of points any player can of a game is allowed to earn, or the speed of light. Naming hard-coded values used throughout a program as constants is useful in conveying the meaning of that value to future maintainers of the code. It also helps to have only one place in your code. You would need to change if the hard-coded value needed to be updated in the future is needed to be updated in the future. Shadowing, as you saw in the guessing game tutorial in chapter 2, you can declare a new variable with the same name as the previous one, as the previous variable. The stations say that the first variable is shadowed by the second, which means that the second variable is what the compiler will see. When you use the name of the variable in effect, the second variable overshadows the first, or first variable is shadowed, or second variable shadows the first, or overshadows the first, taking any uses of the variable name to itself until either it itself is shadowed or the scope ends. You can shadow a variable by using the same variable's name and repeating the use of the let keyword as follows. So let x equal to x and 2, so it will be 2, I think. Value of x is copy this, and okay, I will check. I will run 12, and this is 6. No, yeah, 6. 6, this is 12, This is 6. And the first, this program binds first binds x to a value of 5, then it creates a new variable x by repeating x equal to, then creating the original value and adding 1. So the value is 6, then 6. Then within an inner loop created with the curly brackets or curly braces, the third let statement also shadows x and creates a new variable multiplying the previous value by 2. X a value of 12. When that scope is over, the inner shadowing ends and x returns to being 6 when we run this program. It will output the following. Shadowing is different from marking a variable as mutable because we get a compile time error if we accidentally try to reassign this to this without using the left here. So shadowing is different. You need to use that keyword, and in mutation, you don't have to use let keyword. It's the same variable. So by using let, we can perform a few transformations on a value, but have the variable be immutable after those transformations have been completed. So the other difference between mutable and shadowing is that because you are effectively creating a new variable, the old variable is gone again. So when you use the let keyword again, we can change the type of the value, but reuse the same name. For example, say our program asks the user to show how many spaces they want between some text by inputting space characters, and then we want to store that input as a number. The first spaces variable is a string, and the second spaces variable is a number type. Shadowing thus spaces from having to come up with different names such as spaces string and spaces number. Instead of reuse the simplest spaces name, however, we try to use mutation for this, as shown here, we'll get a compile error. Interesting. So copy this. Expected string found unsigned cells. So if you remove let, it's gone. If you put let but mutate, you say mutable. Um, you can do this, but then this is not actually. This is actually a mutable string, and this is the length. Alright. Alright, I'm sleepy, so I'm just gonna go ahead and stop here. But before that, okay, so expect this is mutable spaces, so you can actually mutate it, change it into a string, but can you actually say let again? Can it be okay? It can be shadowed, so but this is not being used though, but it can be shadowed. If you actually do this, mutate, you say mutable, but then you actually assign spaces, which is a string, a value of unsigned. This is when you actually unsigned size, right? Then that's wrong. This is you're not allowed to mutate a variable's type. You can mutate the variable's uh, value, but not the variable's type. So you can change the value to a value of the same type. So the first series variable is string type, the second series is number type, arrowing thus spaces from having to come up with series string num, and if you try to use you'll get a compiler. The error says you're not allowed to mutate a variable's type. So, mismatch types. Now that you've explored how variables work, let's look at more data types they can have over here. Let's look at the data types in the next video. That's the next one. Bye.